my earlier video, I had discussed about some question of linear algebra which had come different type of competitive exam. Today I will discuss this type of question again because actually linear algebras are very important for any competitive exam. First question, this is very conceptual question which had come December 2017 exam. The question is, here one set which is considerable as capital M. The set is denoted as such matrix A, consider one arbitrary matrix A, B, C, D, but here restriction A, B, C, D belongs to Z. That means all entries belongs to integer. And other restriction, here all eigenvalues of R in the Q. That means here all eigenvalues belongs to rational number. Then option 1, M is empty. Option 2, M equal to set of those matrices A, B, C, D where A, B, C, D belongs to integer. Notice here difference between this M and this set. Here also exists other restriction. Here all eigenvalues of A are in rational number, but here there exists no restriction about eigenvalue. And option 3 indicate if A belongs to M, then eigenvalue are in Z. Here given the eigenvalues of A are in rational number, but here given the eigenvalues only with the integer. And we all of us know Z means always rational number. Okay. And option 4 indicate if AB belongs to M are such that AB equal to identity, then determinant of A plus 1 minus 1. First, try to own self. Then, see my solution. Let's see the solution. First, M is empty. Is it true? Consider identity matrix or null matrix. Here all entries be integer and eigenvalue here 1. So obviously this belongs to Q. So M is empty. This is not true. So option 1 is a wrong option. And notice the option 2. This is very important option. Here has indicate M equal to set of those matrices whose entries be integer. But here there exists other restriction also, which I have told you few minutes ago. Here there exists other restriction, eigenvalues of A always be the Q. Now notice one matrix M equal to 0, 0, minus 1, 0. Sorry, here 1. Here obviously the characteristic polynomial of this matrix is x square plus 1 equal to 0. That means eigenvalue is plus minus I. But notice here all entries belongs to integer. So we can assume this matrix for this set. But this set not belongs to this set. So option 2 also wrong option. Okay. And option 3 indicate if A belongs to M, then eigenvalues are all integer. That means we have to prove here all eigenvalue belongs to integer. And integer means obviously this is belongs to Q. Eigenvalue means the root of the characteristic polynomial And actually this property depends on abstract algebra. Since the characteristic polynomial always would be monic polynomial, so by the property of abstract algebra, this root always belongs to integer. And the proof is such type. Consider this polynomial where ai belongs to integer and assume the root belongs to rational number, means p over q, where p belongs to integer and q belongs to integer. And we all of us know if p over q be the root of this equation, then p divide a naught and q divide a n. And since characteristic polynomial is monic polynomial, that means obviously a n would be plus 1 or minus 1. That means obviously q divide the set 1 minus 1. And if q divide the set 1 minus 1, that means the root actually equal to p. So if the polynomial be the monic polynomial, so always the root be the member of integer. And actually this property will be hold here. Here, since a belongs to m, then eigenvalues of a are in Z. Obviously this is true. By concept of algebra we can tell easily, and by concept of linear algebra this proof would be, consider m equal to this matrix where a b c d belongs to integer and eigenvalue of a in the rational number, and consider a belongs to m, then we have to prove lambda a means eigenvalue be the member of integer. And consider the characteristic equation would be such type x square plus bx plus c equal to 0, and here the eigenvalue in the rational number, and we have to prove this eigenvalue is actually nothing but only integer. And we all of us know determinant means product of the eigenvalue, which is actually c. That imply actually each eigenvalue always divide c. And notice here c be the integer. That means each eigenvalue since divide one integer, that means obviously this lambda I, each lambda I belongs to integer. Are you getting? That means our proof has done. If a belongs to m, then this eigenvalue is actually integer. Okay? Oh well. Fourth option is actually obviously true, because this option I have discussed in my previous lecture. If AB belongs to M such that AB equal to I, then determinant of A only the set containing plus 1 minus 1. Okay? This is obviously true. Just recall my previous video. Recall again, AB equal to identity means obviously B equal to A inverse. And I have seen one result. If A be n cross n matrix over integer, then A inverse also has an integer entries if determinant of A is equal to plus and minus 1. Are you getting why I have told you my previous video is very important to understand every lecture in better way? Okay. Oh well. This type of question is actually very conceptual of question. See, different type of question which had come December 2011 question. This is also basic question. The question is A and B are complex n cross n matrix. Then which of the following statement are true? Option 1. If A, B and A plus B be invertible, then that imply A inverse plus B inverse is invertible. Option 2, if AB and A plus B invertible, then A inverse minus B inverse is invertible. Option 3, if AB is nilpotent, then BA is nilpotent. And option 4, the characteristic polynomial and of AB and BA are equal if A is invertible. This is actually very basic question. That A and B be the n cross n matrix. So just write this. And for option 1, here A, B and A plus B be invertible. That means determinant of A not equal to 0, determinant of B not equal to 0 and determinant of A plus B not equal to 0. We have to prove A inverse plus B inverse is invertible. For this, just multiply, at first pre-multiply A inverse plus B inverse by A and post-multiply A inverse plus B inverse by B. This would be at first A inverse times B, which is actually A inverse means identity, this is equal to B, and this would be A times B inverse B, and B inverse B means actually identity, that means this would be A, that means this is actually A plus B. Now since we have to prove A inverse plus B inverse is invertible, so we have to prove determinant of A inverse plus B inverse is not equal to 0. For this, apply determinant both sides, then this would be determinant of A times determinant of A inverse plus B inverse times determinant of B, which is equal to determinant of A plus B. And given A, B and A plus B is not invertible, so obviously determinant of A not equal to 0, determinant of B not equal to 0 and determinant of A plus B not equal to 0. That means this would be not equal to 0, this is not equal to 0 and this is not equal to 0. That means this implies determinant of A inverse plus B inverse is not equal to 0, since here both be not equal to 0. That means that implies determinant of A inverse plus B inverse is not equal to 0. Are you getting the proof? Oh well. That means option 1 is a right option. Okay. And option 2 imply if A, B and A plus B invertible, then we have to prove A inverse minus B inverse is invertible. Option 2 is similar to option 1, but here we have to prove A inverse minus B inverse is invertible if A, B and A plus B be invertible. For this, consider one example. A equal to identity, B equal to identity. Then obviously A plus B would be 2i. Then A inverse equal would be identity and B inverse also would be identity because these are identity matrix. Then A inverse minus B inverse would be equal to I minus I, which is obviously equal to 0. But this is wrong option because 0 matrix cannot be invertible. Okay. So option 2 is a wrong option. If A, B and A plus B invertible, then A inverse minus B inverse is invertible. This is wrong option. And option 3 indicate if AB is nilpotent, then BA is nilpotent. Just think, basic and very conceptual question. The proof is such type. Here given AB is nilpotent matrix. So obviously by definition AB to the power k equal to 0 for some k belongs to natural number, then we have to prove BA is nilpotent. And BA to the power k plus 1 means actually BA times BA times BA times, this would be continue k plus 1 times. And this means actually B times AB, 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 this would be continue. So I have written AB here k times, then this would be only 1a. Therefore this imply B times AB to the power k times a. And Since AB is nilpotent, so this imply AB to the power k equal to 0 for some k belongs to natural number. That means this is equal to 0. So here I have got b times 0 times a. That means this is obviously equal to 0. And since I have got BA to the power k plus 1 equal to 0, that means obviously BA also nilpotent matrix of index k plus 1. Okay? Option 3 is the right option. If AB is nilpotent, then that implies obviously BA is nilpotent. And option 4 indicate the characteristic polynomial AB and B are all equal if A is invertible. This proves also basic concept. For this, the characteristic polynomial AB is actually determinant of AB minus lambda I. And here we can write this as AB times A inverse minus lambda I times A inverse. And lambda IA, actually this is same as A lambda I. Therefore, this is, we can write this as determinant of A times BA minus lambda I times A inverse. Okay, notice this expression and this expression are both same. And by the property of determinant, this is actually equal to determinant of A times determinant of BA minus lambda I times determinant of A inverse. And determinant of A inverse means actually 1 over determinant of A, just this, omit this part, then this is actually equal to determinant of BA minus lambda I. Okay? So, I have got determinant of BA minus lambda I. This is actually the characteristic polynomial of BA. So, I have got characteristic polynomial of AB and BA both equal. And this is equal because A is invertible, I have assumed. Otherwise, this is not possible. Option 4 is a right option. Characteristic polynomial of AB and B are equal if A is invertible. Are you getting the option? Oh well.